All right, how's everybody doing today? Cool. Okay, fantastic. So today we're going to start with a quick review of Kirchhoff's laws. Remember, there were two of the laws, Kirchhoff's current law and Kirchhoff's voltage law. And these were formal ways of saying things that we kind of already knew. So we'll talk about what those are, and then we'll also talk about voltage dividers. Then we'll go on to the main topic for today, which is Watt's law. We'll talk about what it is. Really, Watt's law is more of a definition than a law. It's really the definition of power, and it just says that power is voltage times current. That's really all that it is. So since it's all about power, we'll talk about what is power, and why is power important in electronics, and then why do you need both voltage and current in order to get power. We'll also see a couple of alternate forms of the Watt's law, and we will do a couple of examples on the board. And then we will also talk about rounding. So we'll talk about what it is, why it's important, and how we use it, and then do a couple of examples of that, and then we'll go on to the preview for today's lab. Okay? And for homework, I'd like you to work on the Watt's law quiz and also the rounding quiz. So any questions before we get going? Yeah.
It says on the schedule Thursday's review for the midterm.
Right.
How's that going to be laid out?
Yeah. Okay. So today is going to be the last day where we're actually learning new material before the midterm. On Thursday, we will do a review for the midterm, and then next Tuesday, a week from today, we'll take the test itself. So on Thursday, when we come in and we do the midterm review, you'll all come here at the normal time. We'll still meet here in the normal place. Same bat time, same bat place, right? But instead of learning new material, we'll just we'll review the questions that will be on the midterm. So I think I mentioned earlier in the semester that really there's going to be one basic circuit for the midterm, and you will be asked to find the voltages and the currents in that circuit. You can do that two ways. You can either do that with math, or you can do it with by building the circuit and making measurements on the circuit itself. So I'll go over both of those ways in class. Yeah?
And the midterm's online?
Well, you will all come here on the day of the midterm, and you'll take it in class, but you will be entering your answers online on the computers.
Okay.
So you still need to come here.
Okay.
Yeah. Yep. So yeah, so that'll be, again, the midterm will be a week from today. So any questions about that? And we'll go over more details next time when we do the review. All right. So then let's do our review of Kirchhoff's laws. So we'll start with Kirchhoff's current law. So Kirchhoff's current law involved wires and junctions. So, and current, of course. So anybody remember what Kirchhoff's current law said? Yeah.
The sum of all currents into a node equals the sum of the current out of a node.
That's right. The sum of the currents flowing into any node is the sum of the currents flowing out. So if we had some wires like this, we could pick this junction right in the middle to be our node. Remember, a node is just any point on the circuit. So we can pick that to be our node, and let's say we had, say, 9 milliamps flowing in here, and 6 milliamps flowing in there, and then we know that we have 10 milliamps flowing there. How much current would be flowing out that way? Well, let's see. So we've got 9 flowing in and 6 flowing in. So how much is that altogether flowing in? 15, right. So we got 15 milliamps flowing in, and then 10 of that flows out down this way. So whatever's left over has to flow out that way. So how much is left?
5.
5, that's right. So we would have 5 milliamps flowing out that way, okay? So that's what Kirchhoff's current law says. Any questions about that?
Could you do like one more example?
Sure. So let's say that we had say we have 12 amps flowing in there. We could pick this as our node. And maybe we have 8 amps flowing that way. How much would be flowing that way?
4 amps.
4 amps, exactly. So, yep. So you just look at all of the currents that are flowing in, and if you add up all of the currents that flow in, they have to be the same as all of the currents that flow out. Basically, another way of saying it is that current does not build up at any point in the circuit. Yeah.
Like on that one, right, if we got the 15, right?
Yep.
Oh, so we minus the 10 because it's going out, right?
Right,
That's
exactly.
why we don't add that in, right?
Right. Mm-hmm.
So the other ones are coming, so they go to the node and then they'll go.
Cool. Yep. Yeah. Any other questions about that? All right. Cool. So that's Kirchhoff's current law. We also talked about Kirchhoff's voltage law, or KVL for short. So what was the definition of Kirchhoff's voltage law?
The sum of all voltages around the loop is 0.
Yeah, that's right. So if we look at a circuit, we can draw any loop that we want, which is just a path that starts and ends in the same place. And if we add up all of the voltages around that loop, they should add up to 0. So let's say that we had a circuit like this, and let's say this is 10 volts across the power supply, and 2 volts up here, and then let's say maybe 3 volts there, and 0.5 volts up there. We want to figure out the unknown voltages in this circuit. So do you think we could do that? Probably. So how could we use Kirchhoff's voltage law to do that? Yep.
You go 10 volts, you got 2 and 3, so you got to have 5 down the bottom, right?
There you go. Perfect. So we could draw a loop here. So we could start there, say, and go around this way and end up back where we started so that we have a loop. And then Kirchhoff's voltage law says that if we add up the voltages around that loop, they should be 0. So just like you said, if we start here, the one tricky part about this is we need to show sort of which side of these voltages are positive and which are negative. so that we know if we're going up or down. So really, it's just the end of the resistor that's closer to the negative side is negative. The end that's closer to the positive terminal of the battery is positive. Okay? So if we go around this loop, we start down here and we go up by 10 volts because we're going uphill. So plus 10 volts, and then we're going across here. So do we add or subtract this voltage? Subtract, because we're going from high to low. We're going downhill. So minus 2 volts, and then minus 3 volts, and then minus our unknown voltage, right, equals 0. So some people are doing the math in their heads, which is awesome. So if we do 10 minus 2, that's 8, minus 3, that's 5. So 5 volts minus our unknown voltage equals 0. So the unknown voltage equals 5 volts. So so this unknown voltage there would be 5 volts. Any questions about how we got that? Okay. And then we could do the same thing for, or a similar thing for this resistor over there. So where could we draw the loop to figure out the voltage across that resistor? Sure, we could do the whole outside. So, so we could start there again, but just for fun, we could start anywhere. So why don't we start up here? So, so we go through here, and then down that way, and then around, and end up back where we started. So, and again, whichever side of the resistor is closer to the positive terminal is usually positive. So we're starting here, and we're subtracting 0.5 volts. So minus 0.5 volts, and then minus our unknown voltage, and then minus 5 volts. And then we go across the power supply. Do we add that or subtract that? Add, because we're going low to high. We're like going uphill. So plus 10 volts, and then
Minus 2.
Yep, exactly, minus 2 volts. And we're back to where we started. So what does all of that add up to? 0, exactly. All right, so so basically 10 minus 2 is 7, minus 5 is 2, and minus 1.5,
Wait,
or,
10
sorry.
minus 2, 8?
Yes, thank you. I'm going a little too fast here for myself. All right, thank you. So 10 minus 2 is 8, minus 5 is 3, minus 0.5, so that's 2.5. So over here we have 2.5 volts minus our unknown equals 0.
2.5.
Right, exactly. So our unknown voltage is 2.5 volts.
Where did the 0.5?
So this up here is 0.5. So yeah, sorry. I'll try and make that a little bit.
It's okay.
Yeah, that's 0.5. So our unknown voltage is 2.5 volts.
Sorry, can you explain from that first equation down to the 2.5 volt, what you did in between there?
Yeah, so what I did is I just added up all of the numbers that we know, and together those all add up to 2.5. Yeah. could we have done this and figured this out by drawing any other loop or a loop in a different place? Yeah, we could have done it over here, for instance, like started there and gone around that way, right? So if we did that, we would have 3 minus a half gives us 2.5 minus our unknown voltage would be 0. So then we would also see that our unknown voltage was 2.5 that way. So yeah, you can draw different loops in different places, but as long as they start and end, as long as it's a loop which starts and ends in the same place, the voltages around that loop should add up to 0. Okay?
And this is, what law is this called?
Kirchhoff's voltage law. Yeah, abbreviated KVL, because nobody remembers how to spell Kirchhoff. I know I don't. Yeah, so any questions about that? All right. Cool. And then the last thing we talked about on last Thursday was we talked about voltage dividers. Yeah?
What lecture topic does the midterm exam go up to?
It goes up to today.
Today?
Yeah. Yeah. So you can use anything that we've learned throughout the semester to try and help you figure out the voltages and currents in that circuit.
Okay.
Yeah. So, so we talked a little bit about voltage dividers last time. We said a voltage divider is really just a fancy name for 2 or more resistors in series. So, say we have a circuit like this. Each one of these resistors is 1 kilo ohm. And we have 15 volts over here. If all of the resistors have the same value, then they all get the same share of the total voltage. So in this case, there are 3 resistors, they're all the same value, so each one gets 1/3 of the total voltage. So if we have 15 volts total, how much voltage do we have across each one? 5, exactly. So we have 5 volts, 5 volts, and 5 volts. So you can see that this circuit is called a voltage divider because it divides the total voltage among the resistors. If the resistors don't have the same value, then basically they each get a share of the total voltage that's proportional to their resistance. So let's say that we had 25 ohms here and 75 ohms down there. And say we had 12 volts there. What would be the total resistance for this circuit? Yeah, it's a series circuit, so the total resistance is just the sum of the individual resistors. So the total resistance is just 100 ohms, okay? So this top resistor would be 1/4 of the total. So it would get 1/4 of the total voltage. So the total voltage there is 12 volts. So this would get 1/4 of that. So what's 1/4 of 12? Right. So that one would get 3 volts. Down here, this one is 3/4 of the total resistance. So it gets 3/4 of the total voltage. So how much would that be?
9.
9 volts. Perfect. So you can divide the voltage that way as well. And we also said that potentiometers act like voltage dividers. So a potentiometer is basically just a very long resistor that has a movable wire, essentially, that can be attached to different points along the resistor. So say that the whole resistance here was 100 ohms, and you attached a wire, up here, so that this was 25 and 75, 25 ohms above the wire, 75 below, then essentially you'd have this same situation that we were just in. Top part would get 1/4 of the total voltage, the bottom part would get 3/4. But the potentiometer, with the potentiometer, you can move this wire around. So you could move it down to the middle. So if I moved it right in the middle, how much resistance would I have at the top here?
50.
Yeah, 50 ohms. And how much down below? 50 ohms, perfect. So, and in that case, we'd have half the resistance above, half the resistance below, so you get half the voltage above and half the voltage below. So a potentiometer is like basically a variable voltage divider. Okay? So questions about that? Yeah.
The voltage divider circuit on the left,
Uh-huh.
we had a rail extended, say, the first and second resistor,
Add a what, I'm sorry?
wire or a rail, I'm not sure.
Yeah, a wire, yeah.
To get 5 volts from the circuit. If we wanted to use that for other components, how would we reckon it? Would we reckon it as a place along the wire with 5 volts and a certain amount of current? Or would we treat it almost as if it was a 5-volt power supply by itself?
Right. So that's a good question. So once we have this circuit here, and say we wanted to get 5 volts from it. So say we attach a wire there, and we attach another wire to ground. So we know that there's 5 volts difference between these two wires. Now, what can we actually do with that? Can we use that as a power supply to power other things, or what? So good question. So let's think about what would happen if we treated it like a power supply. So let's say we had a bunch of lights, and those lights needed 5 volts to power them. So we'll draw a light like that. That'll be a little light bulb. So we could put a bunch of light bulbs here. Something like that, say. And let's think about what would happen there. So these light bulbs are like little resistors, and depending on the light bulb, you might have a resistance of, say, 10 ohms for each light bulb. Okay? So now what you've got here is you've got a parallel circuit with 3 light bulbs, and each one has 10 ohms. So what would be the equivalent resistance of that circuit?
30.
Yeah, about 3 1/3. So that would be like putting a resistor right here that is 3.33 ohms. Okay? Well, now you've got a 3.33 ohm resistor in parallel with a 1 kilo ohm resistor. And we know that when you have two resistors in parallel, the total resistance is going to be less than the smallest one. Okay? So,
Get 3.3.
Yeah, how did you get 3.3 from 310 ohm resistors?
so they're all in parallel. And the resistance of a parallel circuit,
Oh, yeah, you divide 3 by 10, right?
right, is one of those resistors divided by the number of the resistors. Yeah. So that's how we got to the 3.33. So so now you've got this 3.33 in parallel with a 1 kilo ohm resistor. And we know that the equivalent resistance is going to be less than the smallest one. So it's going to be less than 3.33, a little bit less. So we could do the math, but for the sake of argument, let's just call it about 3 ohms, okay? So really, what you've done is you've taken this resistor out and replaced it with just essentially a 3 ohm resistor. Okay? So now, are you still going to have 5 volts, 5 volts, and 5 volts? No. This resistor down here is going to have much less than a third of the total resistance. So it's going to get much less voltage. So this is going to get, maybe a quarter of a volt or something like that. And the rest of the voltage would be up here. So the answer is no, you can't just treat it like a power supply, because if you put things that draw a lot of, or things that have low resistance down here that need a lot of power, basically it pulls this voltage down. So it's not useful for a power supply, but it's often useful for a reference voltage. So for instance, you've probably seen power tools or other things that have rechargeable batteries on them that have little indicator lights that show you whether you have a full charge or half a charge or a low charge, right? Well, that type of circuit can be, or that type of circuit can use a voltage divider. Another type of circuit is an oscillator. So you have, basically you've got different references here. So this would be like 10 volts relative to ground. This would be 5 volts relative to ground. What the circuit does is that in an oscillator, the circuit creates a wave that charges up. And so it starts at 0 here, and it charges up, and it keeps on charging until it reaches this reference up here. And so the circuit has got a little device called a comparator that compares two voltages. It compares this charging voltage with this reference voltage, and when the charging voltage reaches the reference voltage, the circuit flips a switch and starts discharging. And now this voltage goes down and down and down until it gets to this lower reference down here. And then when it gets down there, the circuit flips another switch and it starts charging up again. And so then it keeps on going back and forth between these two reference voltages. So we're not drawing power from this circuit, but we're using those voltages as references. Yeah?
What determines the shape of the waveform for the oscillator?
So the basic waveform inside of the oscillator is determined by the charging of a capacitor. So that, if you looked at the whole wave for that, it would kind of look like this, and it would charge up until it got to some final value. But what we're seeing is just this little part right in the middle here, where it's charging up. And if it discharged, it would look like that. But again, we're just seeing sort of this little part in the middle here. So that's what determines the shape inside of the oscillator chip, or the oscillator circuit. But once you have that, you can use that to create other types of waves. So you can use that to create waves that are more like a square wave, or you could use it to create a sine wave. Basically, if you wanted to do that, you would take this triangle wave as an input and then do other things to it to create these other shapes of waves. Yeah, so that can be used in music to create different tones, because each different wave shape has its own sort of sound to it. And it can be used in other circuits as well. So generally, voltage dividers are used as references, not as power supplies. Yeah. Other questions? Okay. All right. So then let's go on to our main topic, which is Watt's law. So Watt's law is pretty simple. It just says that power equals voltage times current. So that's really all there is to it. It's really more of a definition than, something fancy. So power is voltage times current. That's what Watt's law is. So the next question is, what is power? Well, power is really the amount of work that's being done at any particular instant. Okay. Now, this is important in electronics because we're often using up energy in electronics and doing work. So we could be using power to do useful things like lighting up a light bulb or turning a motor or things like that. But oftentimes, power is also just wasted in our circuits. Power is being used by resistors and just turned into heat. And it's important to be able to calculate that, to calculate the power, whether it's being used for something that we want or whether it's just being wasted. Because even if it's just being wasted, we want to make sure that we're not using too much of it so that our circuits don't overheat. Okay?
What would be the unit used for power?
Yeah, thank you. The unit is watts.
Is there any other units that we would deal with?
Yes. So watts is the most common unit in electronics, but there are other units for power. So horsepower is the other commonly used unit of power. But in electronics, it's almost always watts. So we need to be able to calculate the power, whether we're using that for useful things or whether it's just being dissipated as heat. So why do we actually need voltage and current in order to create power? Well, you can think of this, you can imagine a water wheel, okay? So imagine you've got a big paddle wheel on an axle, and it's being turned by a stream. The stream is flowing down and hitting the water wheel and making it turn. Now remember, with electricity, the amount of electricity that's flowing is like the amount of water that's flowing. It's sort of like gallons per minute. And the pressure, or the voltage in electricity is like the pressure in the stream. So in order to turn that water wheel, you need both a lot of pressure and a lot of volume of flow. If you just have pressure but a very small volume, that wheel's not going to turn very much. And vice versa, if you have a lot of water flowing past, but the pressure is very low, that's also not going to turn the wheel very much. So you need both pressure and volume in order to make that wheel spin. And the same goes in electronics. You need both voltage, which is electronic pressure, and current. You need both of those, voltage and current, in order to make something happen. So that's why power is voltage times current. You need both voltage and current to make the power. Okay? There are also a couple of alternative forms of Watt's law. So if you know the voltage and current, you can calculate the power pretty easily, but sometimes you don't know both of those. So sometimes you know the current and resistance, for instance, and you want to calculate the power. So then you could say power equals I squared times R. So if you just know the current and the resistance, you can do that. Also, if you just know the voltage and the resistance, you could say power is V squared divided by R. So those are both acceptable forms of Watt's law as well. So this is kind of a lot to remember. There's different forms here. But fortunately, there is a drawing in your lab book, or a diagram, that has all of these forms together. So if you look on page 57 in your lab book, there is a diagram that has all of these things. So it looks kind of like this. And it's this big circle. And in the circle, in the middle of the circle, there are voltage, current, power, and resistance. Whatever. So in the middle of the circle, it shows what you want to calculate. And then around the outer part of the circle, it shows the formulas that you can use to calculate that. So for instance, in the bottom right-hand corner, in the middle, there's power. So that's what you can use if you want to calculate power. And then outside that, there are the different forms of Watt's law. So I times V, voltage times current, I squared R, or V squared over R. This also has formulas for calculating resistance, voltage, or current. Okay? So all of those are in this one diagram, so you can check that out. All right. So those are the alternate forms of Watt's law. So any questions about that? All right. And then finally, I wanted to talk a little bit about rounding. Okay? So rounding doesn't sound very interesting, but it's actually very important. It's one of the most commonly used skills that we have in electronics. So that's why I wanted to take a few minutes and talk about it. So sometimes we have numbers that have a lot of digits on the end and we want to approximate them. And that process of approximation is called rounding. So imagine that we have a number 12.7 and we want to approximate it with a whole number. Sort of the easiest thing to do would just be to drop that extra decimal and say, okay, that's about 12 volts, say. But unfortunately, this is wrong. This is not the best way to do that. So let's think about why that is. Basically, if you look, right. And let's see why. So imagine we have a number line here. So we've got 11, 12, 13, and so on. Now we look at 12.7, that's about there. It's between 12 and 13. So it's about there. But if you look at it, it's actually closer to 13 than it is to 12. So if we just wanted to approximate this with one whole number, we would approximate it with 13 because it's closer to 13 than 12. So 12.7 is approximately 13. Okay? It's closer to 13 than 12. So we wouldn't just write 12, we would say 12.7 is about 13. Okay? So the general procedure is we decide how many digits to keep, and then we look at the next, or look at the digit to the right of the smallest that we keep, and then 5 or greater rounds up, and 4 or less rounds down. So let's apply that to this problem we just had. So first of all, we decide how many digits we want to keep. We want to keep just the whole numbers. So we want to keep these 2 digits, or the first 2 digits. So then we look at the digit to the right of the smallest one that we want to keep. So that would be this one here. And then if that's 5 or greater, we round up. So is this 5 or greater? Yeah. So so then we round that up. So that means that it takes the smallest digit we want to keep and it makes it go up by 1. So that becomes 13. Okay? So questions about that? Yeah. It's extremely common. So almost anytime you take a measurement, many times you will have an instrument that is, gives you 5 or 10, digits of precision. And you don't necessarily want to keep all of those. So almost always when you're, so quite frequently when you're taking data, you will have to round.
Because I remember you in the beginning, you were saying how certain resistors can be more expensive because they're more accurate.
Right.
So, like, why wouldn't you want to be, is there just certain electronics that you want to be as accurate as possible, or does it usually not really matter?
Well, so that's a good question. So that kind of comes, it sounds like what you're really asking is how much information do you keep and how much is really important, right? So it kind of depends. So certain it kind of comes down to judgment. So with certain types of measurements, you want to be very, very precise. So like I took a trip up to Agilent, where they have a repair facility up in Roseville, and they do calibrations up there. So they have machines there that are used to calibrate the oscilloscopes and the digital multimeters and things that we use in our labs. So in order to calibrate something, the standard that you're using for that calibration has to be like, I think about 10 times more precise than the thing you're trying to calibrate. So, and they're trying to calibrate some really, really sophisticated machines up there. So they have standards up there that are, precise out to like 10, 15, 20 digits of measurements. So if you're using something like that, you need to keep all of that data, okay? So all of that would be relevant. And when they do the calibrations and when they make their measurements, they probably have a procedure written down to tell you, how many digits of information you want to keep. But even then, maybe their instrument goes to 21 places and you only have to keep 19. You'd still have to do a little bit of rounding there. Whereas with the resistors that we use in class, what's the common tolerance on those resistors? Yeah, about 5%. And those resistors often vary their resistance based on temperature. So with something like that, you might get a measurement that's 1,253.687 ohms or something, right? But you might be looking at that, and you might see that when you breathe on it and warm it up a little bit, it goes to 1,254 point. I'm trying to write and talk at the same time. 54.328 or something like that. So you might see that it's fluctuating up and down by an ohm, for instance. So in that case, you might say, okay, well this I could write down all these digits, but it's going to change. So it's kind of accurate to about plus or minus, in the 1 ohm range. So then you might try and round your number to the nearest ohm or something like that. So for this class, and in general, if there's no other specification, when you're recording data, you want to keep 3 digits. That will mean that your measurement is within 1% of, or your record is within 1% of whatever you measured.
So we could round a resistor like that up to 1,250 and it would still be okay?
Yes, yeah. So, and yeah, that's what I would recommend in this class and in general if there's no other specification. Did you have a question?
Is there a certain temperature
temperature that resistors are like a standard temperature that resistors are measured at?
So again, it kind of depends. So in the facility up at Agilent, yes, they have a whole room that's very specifically temperature controlled. I think it's like 72 degrees, and it's constant throughout the whole room. They can't have a variation of more than 1 degree over the entire place. So they have airflow going the whole time to keep so that there's no, pooling of warm air in one place or another. So in that case, yeah. In other cases, it's much higher. So sometimes you have an instrument that needs to be very precisely controlled, but it's out in the field, and they know that it would be hard to get the temperature down to 72 degrees if something's out in the sun. So sometimes they have little ovens built into these where they heat it up to say 200 degrees. But they know that it's always 200 degrees, and so that way that reduces the resistance fluctuation based on temperature. So there can be specific temperatures, but they vary from application to application. Yeah.
So that's 3 digits after the decimal.
No. So let me talk about that in just a minute. So what I mean here is that you want to keep 3 digits, and let's talk about the ones that are important. So the digits. Let's see. So the digits that are important are the leftmost digits that are not 0. So you want to keep the 3 leftmost digits that are not 0. Okay? I know it's kind of a funny way of saying it, but that's what you want. So in this case, the 3 leftmost digits that are not 0 would be these 3 over here. So if we were going to do this, we would follow our procedure. So we wanted to keep 3 digits, so that would be the first 3. So then we look to the digits to the right of the smallest one, and in this case it's 3 or 4, so that would round down. So this would round to 1,250 ohms.
So you're confusing me on the that are not 0 part. So what if that was a 1,050 ohm resistor? How would that?
Oh, okay. I'm sorry. That don't start. That don't start with 0. Okay. So this becomes important when we're talking about numbers that are decimal or smaller than 1, essentially. So if you have, say, 0.001286, what you would do is you would look at the 3 leftmost zeros or digits that don't start with 0. So basically you would start with you would keep these 3, and then you would round based on this one over here. Okay? The reason for that is these are the numbers that actually provide information. The zeros are just essentially placeholders. So these are the numbers that actually provide information. So if you were going to round this, the 6 over here would be the first digit that we're not going to keep. So would this number round up or round down? up, exactly. So that becomes 0.00129. Okay? So that's what we want to do. It would be wrong to say that this was just 0.001. We'd be throwing away too much information there. Okay? Yeah.
Does that apply the same if we get an answer like 12.63 mega ohms, or, does that the same thing?
Yeah. Yep.
Okay.
So yeah, if it was 12.63 mega ohms, then yeah, you would keep the first 3 digits that don't start with 0. So that would round to 12.6 mega ohms.
Okay, then what about amps? Is it the same with amps too?
Sure. Yep.
If you get with the, what's it, milliamps?
Yep.
It's still 3? Okay.
You're right. Yeah, and that's why we want to ignore these initial zeros, because if you say you had 1.28 3 milliamps, we look at this third digit, that rounds to approximately, 1.28 milliamps. Okay. If we weren't ignoring those initial zeros, we could say that that's 0.001283 amps. If we weren't ignoring those initial zeros, we would just say that that's about 1 milliamp. And so if we weren't ignoring those initial zeros, we'd get different answers based on whether we included the little prefix. So we need to ignore those initial zeros. Okay? So, yeah. So when you're recording data, you want to keep 3 digits. When you're in the middle of a calculation, you actually want to keep 4 digits. So let me show you what I mean. Basically, let me just explain why all of this is important. I know that this is kind of complicated and a bit dry here. So why are we even bothering with all of this? Basically, what we're doing is we're deciding what information is important and how much we need to keep. And basically, the problem is if we throw away too much information, then our answers can be wrong. Okay? If we round things too much, we can end up throwing away too much information and getting bad answers. Okay, just answers that don't make sense. So that's why we're spending this time. That's why it's important to know what to keep and how to keep it, and not throw away too much information. Because we want to be precise. Okay. And when you go out and get a job, this is probably one of the first skills that you'll end up using. If you're getting a job in electronics, one of the first things you'll be doing probably will be recording data. And if you end up recording data badly or throwing too much information away, that's not going to look good. Okay, so this is really important. It's real skills that are used in the real world. So if you are doing a calculation, you want to keep 4 digits while you're doing the calculation. Okay, so for instance, let's say you had a you were making some measurements, and you were trying to write down. Well, okay, so you made a measurement, and you measured a resistor, and you measured 2.964258 ohms, and then you also measured. You made a measurement of current, and on the meter you saw 0.0382971 amps. Okay, and you want to multiply these two together to get the current, or to get the voltage, and then you also want to add on one more voltage that you saw that was 1.82769 volts. Okay, so you want to multiply these two. Well, first of all, you want to write down the measurements that you're actually going to keep from your resistance and your current, and then you want to add on that voltage there. So what number would you write down if you saw this on your multimeter?
2.964.
Yeah. So we just want to keep the first three digits. So this would be 2.96 ohms, and then
So for calculations, you mean just along the sequence of the calculations?
yes,
You'll keep forward.
right during the calculation. Yeah. So and then what would we keep here?
38.2 milliamps.
Yeah, so 0.0, so we're going to ignore this first 0, and then we're going to try and keep the first three digits after that. And then we have to round based on the fourth digit. So this would be 0.0038, and then do we round up or down? Up. So 0.00383 amps. And then plus, what would this voltage round to?
1.8883 volts.
Yeah, exactly. So this 7 rounds up, so that becomes plus 1.838 volts. So now we want to do this calculation. So what do we get if we multiply 2.96 times 0.0383?
For the whole thing.
So, okay, well, we'll get there in just a second. Yeah. So, 828. Thank you. Yeah.
I think what they're asking is
Oh.
why did you do 4 numbers?
Oh, right. I'm sorry. Yeah, thank you. I was losing track. So that'd be 1.83. Thank you. Yeah. Thank you. Is that better? Good. Yeah. Okay, so if we multiply 2.96 by that,
1.13368.
say that again? 1.13368. Okay. Volts, and so then that would round. We want to keep 4 digits there, so that would round to 1.134 volts. Because we're in the middle of a calculation, we want to keep 4 plus 1.83 volts. So we add those two together. What do we get when we add those two together? 2.964. 2.964. Okay. And then for the final answer, we want to keep 3 digits. So
So 2.96.
yeah, so that would round to 2.96.
Is it coincidence that that's the same as the O?
Same as the what?
That we started out with?
Yeah, it's a coincidence. Yeah. So that's what we would do. So when we record data, we keep 3 digits. When we're doing calculations, we keep 4 digits, and then our final answer we round to 3 digits. Okay? So that's good for this class. That's generally a good principle, unless a particular job specifies something else. Okay? So that's what I wanted to say about rounding. I know that that's kind of in depth, but like I said, it's important to keep enough information that we're not making too big of an approximation. We're not throwing too much away. So for today's lab, we're going to do the Watt's Law lab that is on page 93 in your lab book. So in this lab, the first thing that we're going to do is some multisim. So what we have here is basically a pretty simple circuit. We've got a power supply, and we've got a single resistor, and then we have several meters hooked up. Okay, so over here, we have a meter that's hooked up in parallel with this resistor. In other words, it's measuring something on one side of the resistor and the other. So what do you think that would be measuring? Voltage, exactly. When we have the meter hooked up in parallel and we're measuring a difference between one side of the resistor and the other, we're measuring voltage. Over here, we have a meter that's hooked up in series with this resistor. So what do you think this meter would be measuring? Current, exactly. Since it's in series, any current that flows through the resistor would flow through the meter as well. So in parallel, we're measuring resistance. In voltage. In series, we're measuring current. So we've seen these two meters before, but now up here we have a different type of meter that we haven't seen. So this meter has 2 probes that are measuring in parallel with this resistor. So what do you think those 2 are measuring? They're measuring a difference. They're measuring voltage. They're measuring across that resistor. So these 2 probes are measuring the voltage for that resistor, but then it also has probes that are in series. So what do you think those probes are measuring? Yeah.
What page is this? 93?
93, yeah, in the lab book. So the lab books that came from the publisher, it's on page 93. There were some that were printed here at school that have different page numberings. So this meter is measuring the voltage across that resistor. It's also measuring the current through that resistor. So this meter is measuring voltage and current. So what do you think it's going to do for it? Yeah, exactly. It's power. It's measuring the power for that circuit. So we're using this one to measure voltage, this one to measure current, and that meter to measure power. So we can open up. So what you're going to do is you're going to record your values down here on this chart. So you're going to record the voltage. That's just the voltage here. you're going to use this meter to measure the resistor voltage, this meter to measure the current, and then you're going to calculate the power by multiplying, using Watt's law, multiplying the voltage times the current. So you'll just do that calculation there, and then you will open up the meter and compare your calculated power to the measured power from the meter. So you'll write that down, and then you'll do the same thing. You'll change the resistance values, and you will fill in that table there. So any questions about that? Yeah. Okay, yeah. So you're going to fill out this table. So you're going to get the voltage from this power supply there. That's the battery voltage. The resistor voltage will come from this meter here. The current will come from this meter over there. And then knowing the voltage and current, you'll multiply those two together to calculate the power. And then once you have calculated the power, you'll also measure the power using this meter up here, and you'll compare your calculated power to the measured power. Okay? Yeah?
I just want to double check the formula. Is it V times I or V times I squared?
V times I.
Okay.
Yeah. So that's the basic form of Watt's law. Down here, there's another form of Watt's law, which is I squared times R. So next, you're going to use this other form, this I squared times R. So you're going to open a different circuit in Multisim. It's very similar, but in this case, you're going to just measure the current, and you're going to use the I squared times R form of Watt's law and compare that to the meter power. And then down here, you're going to use the third form, the V squared divided by R. So you're just going to measure the voltage in this case, and you're going to know the resistance, and you're going to do the calculation by doing V squared divided by R, and then compare that to the meter power. Okay? So that's going to be the Multisim part of the lab. Any questions about that? All right. And then next, you're going to build a circuit on a lamp board. So it's the same lamp boards that we've used before, but in this case, you're just going to use 2 of the lamps. You're going to hook up a circuit like this. Then you're going to use a DMM to find the voltage across lamp 1, voltage across lamp 2. You're also going to measure the total current. And then you're going to do some calculations here and calculate the power in this circuit. A couple more calculations on the other side with the power, and that's it for the lamp board. So questions about that? Okay. And then finally, you're going to build a circuit on a breadboard. So again, it's a fairly simple circuit. It's just got a power supply and a resistor, but you're going to measure the current and the voltage for this circuit, and then you're going to calculate the power using Watt's law again. So any questions about that? All right. And that's the lab for today. So I'll take attendance, and then I'll let you go.